This presentation is an internal instability case history that occurred at Brodhead Dam. The presentation was adapted from slides provided by the now retired Jim Talbot of the USDA Soil Conservation Service. The presentation will cover an overview of the dam, a summary of the incident investigation, the findings of that investigation, and the repairs that were performed to address the damage. First, an overview of the dam. U.S. Soil Conservation Service, now NRCS, Dam PA 463, Brodhead Dam, also known as Levitt Branch Dam, is located in north-central Pennsylvania in Monroe County. The project is a dry dam that helps regulate the flow of the Levitt Branch, one of the headwaters of Brodhead Creek, and impounds 1,544 acre-feet. The earth embankment is 90 feet tall with 1 vertical by 3.75 horizontal upstream slope and a 1 vertical on 3.5 horizontal downstream slope. The dam was constructed from broadly graded glacial till consisting of non-plastic silty sand with gravel, cobbles, and boulders. The foundation rock is shale and silty shale. Maximum particle sizes are 6 inches for Zone 1 and 15 inches for Zone 3. The Zone 2 fill consisted of cobbles and boulders. An internal drainage system consists of drainage fill placed on the downstream slope of the cutoff trench excavation and a tow drain placed in the downstream shell. The dam profile is shown in the top right figure. This dam profile was replotted on a 1:1 scale as shown in the bottom figure. The left abutment was steep with a slope approximately equal to 1 horizontal on 1 vertical. This figure shows the location of a gravel blanket drain that was placed over the left downstream abutment rock. The drain started about 20 feet downstream of the dam center line and extends 210 feet to 12-inch drain pipes. The Zone 1 embankment soil is broadly graded with 30% fines, 50% sand, and 20% gravel, with approximately 15 to 20% cobbles and boulders. The drain was supposed to be designed using Soil Conservation Service criteria in effect at the time from 1968. The SCS design criteria required the filter be designed using a gradation curve for base material finer than 1 inch. The investigation of the incident in question is described in the following slides. A large flood event rapidly filled the reservoir behind Brodhead Dam on April 18, 1984. On May 4th, a large sinkhole was observed at Station 4+13 on the downstream side of the embankment, about 160 feet downstream of the center line. The sinkhole was about 6 feet in diameter and 4 feet deep. The sinkhole was investigated using a backhoe. That excavation revealed a large system of cavities, with some of the cavities being horizontal in nature. In response to these findings, excavation with heavy equipment was started to find the extent of the problem. Numerous cavities were found during the excavation. This hole was 28 feet deep and 6 feet in diameter. The cavities were carefully excavated and traced to study the source of the problem. Some of the cavities were up to 10 feet in diameter. It was discovered that most of the cavities originated above the steep shale left abutment. As the excavation progressed, more and more large cavities were revealed. The yellow dots on the figure show sinkhole locations. They appear to be associated with a blanket drain near the left abutment and the steep rock slope on the abutment. Here are the voids viewed in section. It's estimated that approximately 250 cubic yards of material was missing from the embankment. And at most locations, the finer portion of fill was missing, with the coarse portion left in the bottom of the cavity. Even with so much material missing, no visible signs of sediment or lost fill from the cavities was observed at the drain outlets. Once the numerous voids were discovered during excavation, a decision was made to quickly breach the dam prior to a new storm. You can see how steep the left abutment is in the background of this photo. The next few slides will discuss the findings of the investigation. The embankment fill was found to be near optimum water content and well compacted. A ripper was required to be used to assist the excavation for the quick breach. During the investigation, it was found that the embankment fill was internally unstable, with fines and fine sands washing out of the embankment, leaving coarse sand and gravel behind. The embankment soils fall within Sherrard's bands of gradation envelopes of unstable broadly graded soils. On the steep left abutment, the cutoff trench was excavated into solid rock, but the shale was not treated or excavated to solid rock upstream of the cutoff. At the upstream slope contact with the abutment, the exposed shale rock is weathered with many joints. So water flowing from the steep, jointed, and fractured bedrock in the left abutment was thought to have caused the internal erosion. The blanket drain for the embankment was excavated and investigated. This photo shows the coarseness of the drain compared to the adjacent material. It was also found that the Phase 1 inspection of the dam that occurred in 1978 suggested that there was a design deficiency in the filter drainage system, with fines being observed exiting the ends of the drain pipes. For broadly graded materials prone to internal instability, the design of the filter should have been based on the mobile fraction of the base material rather than the total fraction. Had the filter design taken into account the internal instability of the base soil, this incident may have been avoided. The maximum D15 of the filter of the drain should have been less than 0.7 millimeters. The drain outlet collector pipe was a perforated corrugated metal pipe surrounded by coarse drain material. Finally, after much excavation and investigation, the lost fines were found below the bottom half of the pipe in the drain material. The drain outlet pipe was also half full from fines from the fill, so it was concluded that voids in open gravel and cobble zones were created in the embankment from the washing of fines and fine sand from the soil mass. The fines and fine sands were deposited in the drainage fill materials, and some of the fines may have washed through drains and discharged into the downstream channel. The cavities were enlarged upward by caving of the ceiling or stoping. Here's a summary of the erosion mechanism that occurred. Water entered the fractured rock upstream and developed full reservoir head on the upstream side of the cutoff trench. The steep left abutment rock caused the dam to crack due to differential settlement and/or hydraulic fracture due to low confining stress. A high gradient flow through the cracks eroded the non-plastic fine portion of the broadly graded embankment fill, and the drain material was too coarse to act as a proper filter and allowed erosion to continue. Sufficient void capacity in the drainage layer held the eroded soil without having observable cloudy seepage downstream, and finally sinkholes were formed by progressive caving or stoping. To conclude, we'll briefly discuss the repairs that were performed to address the damaged embankment. The recommended repairs included flattening and treating of the rock abutment with dental grout, removal of the drainage blanket fill, grouting of the core trench drain, rebuilding the embankment using revised zoning and fill placement requirements, and installing a properly designed chimney drain across the entire valley. Here's a photo of the breach area prior to the repair. Weathered rock was removed from the steep left abutment and the slope was flattened. Grouting was performed from the surface of the dam to fill the coarse filter on the downstream side of the cutoff trench. Next, the breach was backfilled and properly compacted. Finally, the downstream section of the dam was cut back to a 1.5 horizontal to 1 vertical slope, and a new embankment filter drain was installed the full length of the dam. The result of SCS studies on filters and experiences using broadly graded soil caused the criteria for the design of filters to be modified as recommended in Sherrard and Dunnigan, 1985. To summarize the design issues at Brodhead Dam, the dam had broadly graded, internally unstable embankment soils with non-plastic fines. The fractured rock foundation was not properly treated, and the steep left abutment slope was not properly excavated and graded. There was no full-height chimney filter in the embankment, and the drains were not properly designed and were too coarse to prevent erosion. This concludes the internal instability case study for Brodhead Dam.